So following on from last video, we have here this expression that we got where we have our change in Gibbs energy, which is really what we're interested in, knowing whether the reaction is spontaneous, know how long it'll stay spontaneous. And now we've put everything in terms of a single variable here, which is this change in extent of reaction. We can go ahead and factor this out, and we'll get a bunch of terms times d psi, so that dg, and just as a reminder, all of this is at constant temperature and pressure. We'll have all of these stoichiometric terms and their chemical potentials in this term here, right, where they're negative for the reactants and positive for the products. Times d psi, our extent of reaction. Okay, and so at this point, now that we have everything in terms of one variable, chemical potential, not chemical potential, the extent of reaction, the chemical potentials are showing up here. Let's look at how does the partial derivative of Gibbs energy with respect to this variable, what does that look like? Holding temperature and pressure constant. Well, that's just going to be equal to all of this, right? All of these terms here. So we can write that this partial derivative is equal to, and I'm switching things around here. Yeah, I'm going to put the products first as the positive values. And incidentally, this is why you learned in general chemistry you take products minus reactants, right? It's because of this. So we have nu y, chemical potential of y, plus mu z, chemical potential of z, and just to reiterate, these values here, these are just the stoichiometric coefficients from the reaction. We just have to take those into account. And then we subtract our chemical potentials for A and B, which are our reactants in this case. Okay, and so this gives us how does the Gibbs energy change as the reaction proceeds. If we start with, for example, with just reactants, dg d psi will tell us as the reaction proceeds, is G increasing, decreasing, is it staying the same? And what we want is we want to understand, if dg is negative, then the reaction will proceed, it'll be spontaneous until we reach equilibrium when dg d psi equals 0, and that'll happen at some particular value of psi. Some certain extent of the reaction has happened. Now, for some reactions, that'll be, everything will have turned into products at that point. For some reactions, it'll only go about halfway, and so for some reactions, it'll hardly happen at all. We'll characterize, we'll see how we can characterize these different types of reactions where we have very little reaction that happens, or a moderate amount, or it goes completely to products. Okay, so let's go ahead and define, change some terminology here. So not change some terminology, but define this. This partial derivative is a really important value, and so we call this delta Rg. R meaning reaction, and this is what's the change in Gibbs energy for our reaction. And this is not a constant value. This is something that's going to be changing over the course of the reaction. And so that is equal to our values for the products minus the reactants. So we have this equation here. So we have products here minus the reactants here. Okay, now just as a reminder, we're doing this for gas phase only, so we can now start substituting things, right? If we want to understand how Gibbs energy changes for a reaction, we have a bunch of chemical potentials, and we know that the chemical potential for an ideal gas we can write as mu j equals mu j naught, right? This is a standard chemical potential, plus RT natural log of P over P naught. If we, and Pj. And if we weren't doing this under ideal conditions, we would just substitute fugicities instead of just using partial pressures for gases. Okay, so now let's go ahead and use this definition of chemical potential, put it into all these spots here in our equation, right, our 4 different chemical potentials we have for this particular reaction, and see what we get. And it's going to get messy, but hold on, it'll be useful. Okay, So delta RG. So first what I'm going to do is all of the standard values, these are just constants, I'm just going to pull those out at the front of the equation. So delta RG is equal to, I'm going to put them in brackets here, we'll have the stoichiometric coefficient for y times mu y naught plus the same thing for z plus minus the same thing for a minus the same thing for b. Okay, so those are all the standard chemical potential values, right? So those I've just pulled out. They're all constants. They're all just going to be on their own at the front of the equation. And then we'll have all of the RT all of the second terms, right? All of these terms. I'm going to lump these together as well. So we'll have RT times, nope, not the chemical potential. We'll have the stoichiometric coefficient for y times natural log of py over p naught. And remember, p naught is the same for all these as 1 bar. That's how we define this. Stoichiometric coefficient for z, natural log of p z over p naught, plus the stoichiometric, oh, not plus, that's minus, minus the stoichiometric coefficient for a, natural log of pa over p naught, minus mu b over log pb over p naught. Phew. All right, that's our whole equation. So how can we manage this? How can we maybe simplify a little bit? Well, one thing we can do is all of these terms at the front that I've sort of separated out that are the standard chemical potentials, we can combine this into one term that we define as the standard change in Gibbs free energy for the reaction. So we call this delta RG naught, right? So this is the standard change in Gibbs energy for the reaction. And what you can think of this is this would be the change in the Gibbs energy for the reaction if everything was done under standard conditions. If all the partial pressures of all the gases were equal to 1 bar, this would be the delta G value for that reaction. It could be positive, it could be negative, it could be 0, probably not 0 usually. But that is, we will define as, use the stoichiometric coefficients, y, and multiply them by the standard Gibbs, chemical potential, which is basically the molar Gibbs energy for these pure gases. Right, so we just define it this way. And if we do that, we can also combine. So that's one thing, right? So our delta G of the reaction that's not standard, right? Just delta GR is equal to delta GR naught plus RT, etc. I'm skipping that for now. In the next video, we'll look at simplifying that second expression. Right, so all these other terms down here that I'll highlight in blue, we can combine these into something else that's incredibly useful for understanding equilibria for reactions.